Hello everyone, I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. In this lecture, we will explore the concept of the circular economy in built environments, essentially looking at how we can transform our building industry from a wasteful linear system into a more sustainable circular one. Many books on circular economy are available, and these two books are recommended for those who may want to learn more details. This slide shows growing global resource extraction in the past. This data helps us understand why a circular approach is urgent. There are growing trends of resource extraction of metal, highlighted in dark blue, fossil energy in orange, biomass in green, and non-metal minerals in light blue. As of 2020, annual global resource extraction reached approximately 82 billion tons, while the resource extraction in 1980 was 40 billion tons. Over the past 40 years, the world's raw material extraction used for the built environment has doubled. Such exponential growth in raw material use leads to resource depletion, ecosystem destruction, and high environmental emissions. The circular economy framework emerges as a solution to bend the curve of material use by designing processes that keep resources circulating so we don't have to keep extracting resources at such high rates. The flip side of massive resource input is the output of waste in our built environment. The building sector is a major contributor to solid waste from construction and demolition activities. For example, in the United States, around 615 million tons of solid waste were generated in 2008. 160 million tons, or 26% of the total solid waste, comes from construction and demolition (C&D) waste, including waste from demolishing old buildings, scraps from new construction, and renovation waste. Alarmingly, only about 20-30% of that C&D waste, roughly 32-48 million tons, was recycled or reused, while 70-80%, around 128 million tons, was discarded and sent to landfills. The waste stream from building activities is composed of materials that in many cases could be recovered. About 40% of the discarded C&D waste consisted of lumber, wood, 14% was asphalt materials like old roofing and paving, 11% was soil and fines from site excavation, another 11% was concrete, rock, and brick rubble, around 10% was gypsum drywall, and the remaining 14% was other construction materials. These figures make it clear that the construction industry has a huge opportunity to improve. Most building materials are not inherently waste. Wood, bricks, metals, concrete, and drywall can be recycled or reused. However, under our current linear model, the majority ends up wasted. This slide compares three models of resource flows. In a traditional linear economy on the left, we take materials from the earth, make products from them, and eventually dispose of them as waste. This take, make, dispose process is inherently wasteful. The construction sector often follows this linear path. We extract raw materials, build structures, and demolish them decades later, sending most waste to landfill. The recycling economy shown in the middle is like the linear economy with take, make, dispose process, but integrates a recycling process after use. While this model reduces waste, it still generates waste for materials that are not recycled. The circular economy shown on the right, by contrast, is a regenerative approach where we design out reuse and recycle of waste materials from the start of the project and turn waste into resources. The goal of a circular economy means that materials never truly become waste, but are continually cycled back into use. A circular economy framework for the built environment seeks to turn our linear end-of-life mindset into a circular flow where buildings and materials are part of an ongoing cycle rather than a dead-end waste stream. The circular economy in construction stops waste and pollution before they happen. To move toward the circular economy, it helps to view a building through a life cycle assessment (LCA) lens. Throughout a building's life cycle, from the extraction of raw materials to manufacturing of building products to transportation construction, the years of building operation, and finally demolition or deconstruction. There are constant inputs of resources and outputs of pollutants and waste. On the input side, each phase across the building's life cycle consumes vast amounts of raw materials, energy, and water over their lifetime. On the output side, each phase across the building's life cycle results in emissions and pollutants to air, water, and soil, as well as solid and liquid waste. The European standard EN 15978/2011 provides a structured framework for assessing these life cycle stages of buildings. Using such an LCA framework, we can quantify the environmental impacts at each phase and identify where to intervene with more sustainable practices. Importantly, a circular economy approach introduces strategies at every stage of the life cycle to minimize inputs and eliminate harmful outputs. This holistic view sets the stage for implementing a circular economy in practice. It's about intervening in each life cycle phase to achieve a sustainable loop. Now let's talk about a circular economy approach for the built environment. The graphic on this slide illustrates the concept as a circular loop. The circular economy turns waste into resources and eliminates waste. First, reducing resource consumption from major sectors like building construction, industry, and transportation is important for minimizing the take of resources. This involves designing buildings that require fewer raw materials and less energy to build and operate, and avoiding excess or inefficiency. Next, we implement reuse and recycling of waste and regeneration of resources. In other words, ensuring that the waste outputs of our buildings are put back into the system as resources. When we achieve the proper balance by minimizing input and circulating outputs in the closed-loop system, we approach net zero waste in construction, where waste is eliminated as we continuously loop materials back into use. Net zero waste means that virtually nothing from the building process permanently leaves the cycle. Everything in the built environment can be reused, recycled, or safely returned to the environment. Up to now, we've identified the problems of the linear model and discussed the framework for a circular approach. To truly embrace a circular economy in building, we need to rethink the entire building paradigm. The horizontal axis represents the progression of construction elements from the recycling of individual building materials to the reuse of systems and modules, and ultimately to the adaptive reuse of entire buildings. The vertical axis represents the levels of circularity. As circularity increases, both environmental and economic value increases. The adaptive reuse offers the highest benefits by preserving the entire building. In a circular economy, building materials such as crushed concrete and gypsum boards could be recycled to create new construction materials. Building elements such as used bricks and used windows can be reused to produce recycled or reused materials for renovation and new construction. Building systems such as used facade systems and structural frames could be reused for new facade claddings and structures elsewhere. Building modules such as whole rooms or units can be disassembled and reassembled to form new building modules for adaptive reuse or new construction. Adaptive reuse means nearly all the material and effort that went into the building is preserved when it serves a new purpose. Moving beyond the mindset that buildings have a fixed end of life, we should design buildings with circular use in mind. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future through circular economy practices in the built environment.